Hi there, welcome to this lecture series on matrix algebra. This is lecture 20, part 2, and the topic is on determinant. And this is the third lecture on determinant. And this will be the final part of all the lectures on determinant. So here we will talk about using the determinant to compute the inverse of a matrix, and in the end, we will derive the famous Cramer's rule to solve a linear system. Okay, let's get started. Let's take an example to show that we can use the determinants to find the inverse. So let's say we have an A matrix here, which is 3 by 3, looking like this, and we call the coefficients Aij. And then we can form this matrix using the cofactors as follows. We call the matrix C, and then it's a 3 by 3 matrix. And it looks like this, but it takes a lot of computation to reach here. So what are each element in this matrix? Well, these are exactly the cofactors C, I, J. Now we can recall the formula to compute the Cij. It will be -1 to the power I plus j, so it's either positive or negative in the front, and then the determinant of this submatrix Mij, where you remove the ith row and the jth column, so it becomes smaller. So for example, the first one, C11, this number here would be -1 to 2, so which this will be 1, and then the determinant of M11, where M11 is formed by removing this row, first row, and this column, the first column. So you will have this matrix 2 by 2, and the determinant would be 3 minus -2, so it's 5. Okay, so this is 5 and this is 1, so C11 would be 5. And each of these is computed following this same formula. Now let's observe some interesting property of this C here, at least in this example. So we have an A and we have computed the C on the previous page, and let's do the calculation of A times C transpose. So this is the A, and this is the C transposed. I take the C and transposed it, and then I carry out this matrix production. You can easily do that. We have learned how to do it, so I'm not going into the details. And you can pause and work out just to be confirmed that this is true, that you will get this diagonal matrix, and which has 15 on the diagonal, the same number, which means we could take this number out, and then what remains is the identity matrix. And now we can take this identity, this equal that, and divide both sides by 15. And I can put 1 over 15 in front of the C here. Because it's a scalar number, you can place it everywhere. Then I have A times this matrix is identity, which means this one is the inverse of A. So here, at least for this example, we have A inverse will be 1 over 15, the transpose of the matrix of the cofactors. And if you put in the detail, it's this one is here. So you will be wondering, is this a coincidental that we get something like this, or is this a more general property? And in fact, there is some general properties lying beneath that observation. So let's see, if we have an A matrix and we have the matrix of the cofactors and transposed, so let's say A will be this, and then the matrix of the cofactors are like that with the Cij as its element, and then we perform this multiplication. So what we will get is the following. if I consider the diagonal element here, say 1, 1, so is this one and cross that one element-wise multiplying and add them up, and that will give you the determinant of A, and so will be the second position with this one cross that will give you the determinant of A, and in fact all the diagonals will give you the determinant of A, and all the off diagonal elements, say this one cross that, will give you 0, and so all the everything else. And now we can take determinant of A out, which is the scalar number, and what remains is the identity matrix. Okay, so now this gives us a formula for the inverse of an A matrix, because I have A times C transpose divided by determinant of A is identity, and therefore 1 over determinant of A, that's a real number, multiplied by C transpose will be the inverse of A. Now before we prove that, let's go through this example as a motivation. So this example A, and then we have the cofactors computed here. So remember the one way of computing the determinant using the cofactor is exactly multiplying the element of one row here by all their cofactors. So if this is C transpose, it will be the first column, but here in C it will be the first row. So that one will give you the determinant, and then this one and with these cofactors will also give you the determinant, and this one with the cofactors here will also give you the determinant. So that shows you that A times C transpose on the diagonal of that product, you will have the determinant of A. And then another factor would be if you multiply elements of one row by the cofactor of another row, either this one or this one, you will get 0. Okay, we will do a little proof later. So for this example, we will have, let's say, the first row times the first row cofactors. If you work these out, you get 15, which is the determinant of A. And then you can say take the first row here and multiply by the cofactor of the second row. And then you have 2 times 1 plus 0 times 11 minus 2. And then you see that it's 0. And then you also realize that this would be actually exactly the formula of computing the determinant of this matrix. That is, I would take this row and then replace it with this row that the cofactor is being taken out. So take out that one and put 2, 0, 1 and copy the rest. And this calculation is exactly computing the determinant of that. And there we see that 2 rows are the same. Then the determinant must be 0. Okay, so now we see that A times C transpose will always be a diagonal matrix where all the diagonal elements will be the determinant of A, and all the off diagonal will be 0. So even though here we show it in a specific example, you see that it holds for just any general matrices, and this example is for 3 by 3, and you can easily see that it also holds for n by n. Now we're ready to introduce the Cramer's rule. So we want to solve a system of linear equations. Let's say n linear equation and n unknown. So the A matrix is a square matrix. Assuming that A is invertible, that is, the determinant of A is not 0, then I can use the formula to find the inverse of A matrix by the formula of the cofactors. So then the solution X would be A inverse times B, And the A inverse, we write it out, is 1 over determinant of A times C transpose. And C is the matrix of the cofactors. So we know this is A inverse times B. So what does this mean in components? If we write out all the components, x1, x2 to xn, then this right-hand side would be, that's a number, and then C is the cofactor matrix, and B is the right-hand side. Okay, so we can write out all the components. Now let's take a look at the ith row here. So then on the left-hand side, you will have xi, and the right-hand side, we have the constant, and we take out the ith row in C here, and that will multiply by the B vector. Okay, so ith row gives us one equation. So every row gives us an equation. So we're just looking at equation number I in the system. Okay, so we see that, and this shows that xi is computed as this inner product, that divided by determinant of A. Okay, so that would be, let's write it out, C1i times B1 plus C2i times B2 all the way to Cni times Bn. Now we make one more step. That is, we write also the determinant using the formula of cofactors. That will be taking A1i, C1i, so you're expanding in computing the determinant using this column here. And that's the form it will take. So we see in this expression, the cofactors are the same, and what is the difference are these the coefficients in front of it. So more specifically, the denominator here is the determinant of A, and it's computed by expanding using the cofactor of the ith column. And the numerator here is the same as the denominator, where each of the AKI is replaced by this BK. And then we can interpret this numerator here as the determinant of another matrix, let's call it B, which is obtained from matrix A, and we replace the ith column of A with the right-hand side vector B, and let's call this B. And then we will have the formula, the famous Cramer's rule. Xi would equal determinant of this Bi, so B carries an index I, meaning which column it is being replaced. Okay, so determinant of Bi over determinant of A. And this ratio here is the solution for xi. Okay, so let's summarize and put all the results in one page. So we want to solve Ax equal B, where A is a square matrix. And the Cramer's rule says the solution xi for any I from 1 to n is the ratio between the determinant of Bi over the determinant of A, where A is this matrix here, and we can write out its columns to be V1, V2 to Vn. And B is Bi here is a matrix derived from A, where you take away the ith column in A and replace it by the B vector. Okay, so it's an n by n matrix. Okay, let's take an example that use this explicit formula of Cramer's rule to solve in system Ax equal B. So we have Ax equal B, and this is A, and this is B, and then I have three unknowns. Let's write out, and this is the A matrix, and then I know for Cramer's rule we will need to form these three B matrix is B1, B2, and B3. So B1 is formed by replacing the first column of A by the right-hand side here. So I have this right-hand side, and I copy the rest of the A. And then B2 will be replacing the second one by the right-hand side vector. And then B3 will be the third column is the right-hand side vector now. Otherwise, it's copied from A. And then we need to compute the determinant of all these four matrices. And we know how to do that. It takes quite some work, but we patiently work all of them out, and that's what we get. And once that's done, it's much easier now to just find the solution using the formula. X1 will be determinant of B1 over determinant of A, and we put in the value, we'll get 67 over 15. And for X2 is similar, you just get determinant of B2 here, so you get 62 over 15, and then X3 will be negative 61 over 15. Okay, let's give some comments for Cramer's rule. It's a very simple expression for the solution. I mean, once it's explained what is the BI, what is the determinant, I would say it's an elegant formula, and it's useful for analytic purposes. One restriction is that it can only be applied to square matrices A, so n by n system, where the number of equations and the number of unknown are the same. And we also need to assume that the determinant of A is not 0, otherwise you're dividing by 0. Finally, the strongest criticism is that if you have a system n by n matrices and n is rather large, then this is a very, very heavy computation to obtain all those determinants, and definitely not a computationally efficient algorithm. Okay, let's take an example to see that this formula actually can be useful in situations where you have specific curiosity. So now let's see, we have this system here, AX equal B. B is a constant, and then in the A matrix there is one entry which is kind of a parameter. So A matrix would depend on this. We call this T. So we write A as a function of T. So the question now would be, how does the solution X2 depend on T? Okay, so that's a very specific curiosity. Let's see, if I want to find that out, how can I do this? Well, with the Cramer's rule, we can find this out not too complicatedly. So X2 would be the determinant of this B2 over the determinant of A, and where the B2 will be taking the A matrix and replacing the second column by the right-hand side. So I put the right-hand side and I copy the rest of the A. And then we have determinant of A down there. And now we need to work out the determinant of these two matrices. So look at the B. Let's see, it has quite a few zeros. In particular, the second row here have 2 zeros, and the only one element is not 0. So that could be an excellent choice to apply your cofactor formula. So you would take this position, which is 2, times -1. This is position 2, 1. So 2 plus 1. So this will give you -1. And then take this away, take that away, and you have 1, 3, 2, 2, and you compute the determinant, which will be 2 minus 6 is -4. That is the determinant of B2. Okay, and then for the determinant of A, we could take one of the row or column that has 0. Okay, let's say we pick this one, the first row. So the first term is 0, and then we go to the second one. We have a t times -1 to the power 1 plus 2, because this is position 1, 2. So you take this and cross out this row and this column. You have 2, 0, 1, 2, and you find the determinant, which is 4, 2 times 2. Okay, and then the last is this position. You have a 3, you have the -1 to the power 1 plus 3, and then you cross out the first row, third column, and you have this one. Determinant is -2 minus 2 is -4. Okay, so still quite a bit of computation, but it's doable. And then we simplify all these expressions, and we get 2 over t plus 3. You see, so we clearly see that how x2 depends on t. Okay, so let's summarize, and that's the system we're solving, and we found the expression x2 is that. And how does it depend on t? Well, we can try to plot this function here, and then we see that it has a singular point. When t equals -3, you are dividing by 0, and then on the left of it, and you have a function that's increasing and then blows up when it approaches -3, and on the left, and then on the right of that, and you have also an increasing function, and then starting from very huge negative number and comes in, and then as t goes to infinity, it's 0. It approaches 0. Okay, also here -infinity approaches 0. Okay, and we can also note that what happens when t equals -3. Well, we see that when t is -3, the determinant of a is 0. So the system here cannot be solved because a is now not invertible. So we have reached the end of this lecture, and also the end of the discussion on the topic of determinant. And I hope you enjoyed it. And next time we will move on to something called the eigenvalue and eigenvectors. I hope you enjoyed today's lecture, and I'll see you next time.